Good afternoon. Well, we've been studying algebras. In the AF case, you can talk about C-star algebras. You can also talk about the it, it, it's pretty well equivalent and technically simpler to talk about the algebraic inductive limit setting. So you have a sequence of building block algebras. Um, First algebra and the second algebra and the third algebra and so on, each one mapped into the next. And the union is the limit. Well, you know, how many people are familiar with the inductive limit? What the inductive limit is? There are two. It has two aspects. There's the characterization that works for any category, even an abstract category, in terms of a universal property, which determines it uniquely. And then in a concrete category, well, it doesn't always exist. For instance, in the category of finite sets, it certainly wouldn't exist because you have an increasing sequence of finite sets. Then the limit in the category of sets would be the union, but the union isn't finite, so it's not if the sets are distinct elements or getting strictly larger. And so the limit is just not in the category. And if it's an abstract category, then maybe you can't even construct the limit. That's a good question. But if it's a concrete category consisting of sets, and what's a concrete category? Well, you have first of all, you look at the category of sets. Then if your sets have are groups, that means they have an operation, multiplication or addition. And maps, arrows in the category are set maps that preserve the operation. Abigail, does that seem clear? Okay. And if you look at the category of groups, would you say that has inductive limits? Of sequences, you have a sequence of groups. The first one mapping into the second one mapping into the third, and so on. And would you say that, well, to check, I mean, to check, really be able to say definitely whether there's an inductive limit, you have to have a formal definition, right? Either a construction, which you can just do and then say that's the inductive limit, or a definition, which would be in terms of an abstract universal property. So what's the universal property, by the way? Suppose you have a category and a bunch of objects, maps. And then they all map into a particular object, okay? And you have a commutative diagram. That sometimes that's abbreviation for that is just you just put a single arrow instead of all these finite arrows that obviously start at the finite stage. If you put in a single arrow after the three dots, then it's that is assumed to stand for arrows from all the finite stages into the into a test object, into some test object, okay, into some object. And this may or may not be the limit. So what's the condition for something for which there is a commutative diagram, all of maps from the finite stages into it? What's the condition that that a particular test object should be the universal one? Vincent, do you know, are you familiar with elementary category theory? Okay, but this is an abstract category. I'm not quite sure what you mean by projection. Yeah, but I didn't even understand it in the concrete setting. You're saying if you have a bunch of finite dimensional algebras. Yes, but the projections are sort of incidental. It just happens that a finite dimensional algebra has projections or idempotents, right? If it's a full matrix algebra. So I don't know how you can, well, okay, but I don't expect people to make things up on the spur of the moment, okay? But it seems to me it's a question that you might have asked earlier, because we've been talking about inductive limits for some time, right? Well, one strategy is if you don't know what something means, just wait, okay? And eventually you may know what it means. But there's another strategy. You actually actively seek out what it means. For instance, you look it up on your telephone. It takes about 4 seconds, right? Well, that's an exaggeration. To figure out from what Wikipedia says, what is the abstract definition and what is the concrete definition in important cases, well, that might take more than just a few seconds. Yes, there we go. I'm sorry? Well, I'm using dots to refer to whole sets, okay, whole objects, or groups. If we're talking about the category of groups, then a single point means a single group. So that's the schematic notation. Sorry? Well, it's just I think in the language of categories, it's clearest if you say object. Now it's true that if the category is sometimes a set, then the objects are elements of the set, okay? But since the objects may be sets themselves, and the sets themselves have elements, the sets, if the objects are groups, then the elements of the group are not elements of the category, even if even if you're looking at a set of groups. Of course, if you look at all groups, that's not a set, because already too many cardinal numbers, right? That's a good exercise, that there can't be any largest set, because it would have a cardinal number. It would have to be the largest cardinal number. But Cantor, it was hard on him. I think he had trouble, but later. But he proved a really momentous theorem that if you take 2 cardinal numbers and one of them is not equal to 1, and you exponentiate it to some other cardinal power, the power of the exponent is another cardinal number, which makes sense. Take a Cartesian product, but the other cardinal is also not equal to 1. Well, then in fact, even if it's equal to 1, then this exponential is greater than the exponent, okay? So if you specialize, then take the number 2, which is the smallest one, not equal to 1. If you look at 2 to some power, say 3, then that's 2 cubed is 8, right? 8 is strictly bigger than 3. That's an example of Cantor's law, okay? But that Cantor's law also works if the exponent is infinite, an infinite cardinal. Of course, the first exponent can also be an infinite cardinal. If you take a fixed, after all, the exponential is the power is supposed to be just bigger than the exponent. So if you make the thing that's being raised to a power larger, that just makes it easier for the theorem to be true, right? So the strongest version of the theorem is where you take 2 to a certain power. And then, okay, but then the point is that if you have a largest cardinal number, then 2 to that number will be will contradict the fact that it's so large, because it will be strictly large. That's what cardinal arithmetic shows. So it means, but in particular, it just means that because sets are by definition have a cardinal number. Oh, okay. And the definition of cardinal number is what Cantor worked with and was able to prove his theorem. Well, we don't want to have too much of the course rest on Cantor's theorem, right? But I mean, so but I'm just saying that if we're talking about a category, then we should bear in mind that some categories are sets, and some categories, like a group has to be a set, or an algebra has to be a set, or a vector space has to be a set. But a category, if you look at the category of all vector spaces over a fixed field, then that's not a, even if you look at all vector spaces of dimension 1 over a fixed field. If you look at all vector spaces of dimension 0 over a fixed field, then maybe that's a set. Okay, because at least if you have 2 different vector spaces and they're both 0-dimensional, they only have 1 element. Well, it seems to me they're not just isomorphic. You can almost say they're equal. Okay, but if there's if you need to have a basis, if it's a non-zero vector space, then the basis has labels. Okay, and the labels can be anything. So anything can. Anyway, this is it's easy to get into the world of Alice in Wonderland, I guess. But okay, so what's the universal property? If I have this particular test object, which is the which all the finite stage objects map into with arrows in the category. Does anyone want to say? So what you do is you bring in some other test object, okay, and you want to say that this particular test object is somehow it takes precedence over any other test object. So how would that do it? Let me write down some other test object, okay? So when I draw that single arrow, that means I've drawn a whole sequence of arrows from the finite stages, okay? And so what would it mean that that somehow the second test object and the arrow and the maps into it are derivative from the first in the generic sense of the word, are somehow subservient to the universal object? Yes, Rishi? Yeah. So yeah, right. And I guess the first thing is that there should be such a map. There should be such a map, right? That there should be some map such that the maps from the finite stage object into the given test object, the random test object, those should factor through the now the uniqueness. Sometimes you say that if it's a concrete category, sometimes you say that the image of the finite stage things in the test object exhausted, okay, degenerated. And if you say that, then it would follow that this arrow is unique, because I guess you can only rely on that in special cases when you can prove that if I have a generating subset, if you have a concrete object, concrete category so the objects are vector spaces or something. Well, if you have a subset that generates the vector space, any linear map is going to be determined by what it is on the subspace, on the subset, right? The generating subset. So, and so it'll be unique if it is supposed to make this diagram commutative, okay? But you might as well just say it's unique, okay? And then the advantage of doing that is that makes sense in the abstract, completely abstract category. Okay, don't have to say what it means. That it's a whole bunch of maps into some other objects into an object. Don't have to say what it means that the image generates. In fact, that might be a definition of generating. If you say that I have a whole lot of arrows from other objects into this particular object, if they're supposed to, if you want to say what it means that the images generate that, which a priori it doesn't have a meaning. You could just say that whenever you have a map into some other into some other object, it's determined uniquely by looking at the composition with the finite stage maps. Okay, if it's restriction to all the finite stages, or you have a whole bunch of arrows just from random objects, if you have an arrow that and these all go into something, and you want to know what it says that the images generate that, well, you just say that an arrow from this object into any other object is determined if once you have it, it's determined uniquely by the restriction, by the composition with all the other arrows going into it. Okay, so there is a way of defining what generating means, and then you could say that, and then you can notice that what generating means unique, right? So you might it's somehow cutting to the chase, cutting right to the chase. If you just say the arrow is unique, okay? That's the definition of saying that these things that the images generate. Okay, Vincent, is that clear? So that's what so in that case you say that that this particular test object is the universal one, and they call it the inductive limit. Okay, and in different settings you can have different universal properties. It's a different kind of diagram. Like tensor product can be defined by a direct sum, can be defined by a universal property, and it always says that a certain arrow should exist, making something commutative and be unique with that property. And then the bonus is that the object itself is unique. This universal object is unique in the sense if you have another one, then the unique map going in either direction, by definition, which makes things commutative. One of them is the inverse of the other, and it's an isomorphism. You have to prove that, okay? You have to prove that. That's a good exercise. And a good question ahead of time is how many times are you going to have to use the universal property to prove that the two universal objects are isomorphic in this way, preserving the diagram. Well, so of course you're going to say, guess anyone would guess at least two, right? Rishi, was that what you were going to say? Okay, but okay, well think about it. That's it. Exercise is to prove that prove that you have the universal object is unique, say for inductive limit, and keep track of how many times you have to use the universal property. Now, maybe I can give you a hint. It's a way of telling that your proof is wrong. Okay, if you only get two uses, if you only use it twice, then you're wrong. Okay, proof is wrong. That's my take. But I mean, if someone can produce a correct proof using only the two of course, a universal property means it comes in whenever you have whenever you're applying the universal property to another test object. So so you have to have two test objects. And one of them is supposed to be, at least one of them is supposed to be universal, right? Okay, well, now, but that, I suppose that whatever, that every, that the, but the, but the other, so you have the two ones you sort of want to use the universal property for. Then in each case you have the other one, right? Okay. Well, it's like counting combinations of things. You for each and permutations, you have to be a little careful. So for each choice, if you choose this to be the one you're going to apply the universal property to, well, then you have to say which test object you're going to be applying the universal property to. Okay, but how many test objects are there in the picture? We've got two candidates for the inductive limit, right? Two things which have the universal property. Well, that's two objects, right? And even when you specify one of them, there's still two objects. Okay, now, so that's an even broader hint, okay? Yeah, so, and 2 times 2 is what? Okay, so what's the answer? What am I saying? What am I suggesting that the answer might be? Okay. So, now, one of the things I've talked about is the specific class of inductive limit algebras one gets from matrix algebras, okay? If it's a unitary map between matrix algebras over the real or complex numbers, or even over any field, and take algebraic limits, then Glim showed how, and Dick sort of with an explanation, a little more elegant, a little more um, somehow, well, definitely helpful comments by Dijkstra on Glim's theorem proof. Glim showed that if you want to know how many algebras there are in the sense of isomorphism classes, then they're parameterized in a very nice way, right? That's what he showed. And then what I suggested was that we look also at something that Dijkstra mentioned in this paper. And the paper is quite readable, by the way. I would suggest you look at it. Volume 1 of the Journal of Functional Analysis. Come up in 4 seconds, maybe, after you finish typing. In fact, just as keywords, type in Dijkstra Glim. I bet that might do it. Or Dijkstra on Glim. But because the title of this paper was On Some C-Star Algebras Considered by Glim. Okay. And so one of the things Dijkstra did was, besides systematizing in a certain way, in terms of well, what we can now see as K0, the Glim's classification in terms of supernatural numbers, what Dijkstra called generalized integers, and a bit of a smart aleck, a well-known topologist, Larry Smith, suggested that since they include the natural numbers, it will go well beyond and may be called supernatural numbers. That's a good joke. It's better than a joke. So something else he tried once was not such a good joke, but it turned out okay. When he wanted to visit a place in Germany once, when he was visiting Denmark for some time, I think maybe he was there for a year. This was before the European Union. They had the common market. He just went, and then well, it seemed that he didn't have any trouble going either way without his passport. He just left the passport at home and used his Danish insurance card, health insurance. Well, okay, so what's something that Dixmay did beyond the case of Grimm was look at what I'm calling the free-floating algebra, okay? So you look at the, so what's the free-floating algebra over the complex, based on the complex numbers. So you start with some algebra, any algebra, and you construct a new algebra called the free-floating algebra. And if the algebra is already the free-floating algebra of something, one of the properties of this construction is if you start with the free-floating algebra over something, whatever the free-floating construction is, and you do it again, then you get something which is isomorphic, okay? And that's because take infinite matrices over infinite matrices. You have every infinity, if we're just talking about countable infinity, the natural numbers are in one-to-one correspondence with the disjoint union of infinitely many copies, countably many copies of the natural numbers, right? If it's two copies, it's very easy. You take the even numbers and the odd numbers. If you want to get countably many disjoint subsets of the natural numbers, countably many infinite disjoint subsets of the natural numbers, which you add up to everything. Of course, if you can do it in the first place, get countably many disjoint infinite subsets, it should be pretty easy to get them to have union, the whole thing. But you've got to think a little, right? But I guess you can do it. But that shows that it's just a question of how you index the rows and columns. If the entries are the same, then the question of matrix algebras, when they're the same or not, it's a question of indexing the rows and columns, right? So if the rows and columns are indexed by an infinite countably infinite set, well, there's only one such countably infinite set. That's another way of saying it. And so that says that every time you have matrices over any algebra with infinitely many a countable infinity of rows and columns, and you take the usual addition operation, even with the additional multiplication operation, of course, we have to be talking about finitely non-zero entries, right? Finitely many non-zero entries, so that you can always add with arbitrary entries, but because you add entry-wise. But when you multiply, you do the funny arithmetic, right? And that requires. Well, if you just said that only the rows were finite and the columns were not finite, you could still multiply, but you have to check that does give you an algebra. Maybe it does. Okay, maybe that already would give you an algebra. And then you could do it the other way with columns and rows. The columns being finite, and the rows not. Then you get two different algebras. And the question would be, are those isomorphic? Okay, well, one would be isomorphic to the opposite of the other. I don't, well, so I haven't thought too much about that, but you see, everything leads to a question, right? And so, no, well, some questions, they're good questions, they're better questions, and that's a kind of knack. I'm not saying I have the knack, right? I'm not saying that's a good question. You have to think about it before you decide it's a good question. But I'd be interested in whether someone said that that's a good question or not after thinking about it. Maybe even came up with an answer. If you take if instead of saying both rows and columns are finitely non-zero in our free-floating construction, if you say just the rows are finite with zeros everywhere, almost everywhere, and the columns are arbitrary on the one hand, or if you said the rows are arbitrary, but the columns are supposed to be finitely non-zero, then you get, if it does work out, then both give you algebras, then it's the multiplication associated and so on. Can you Because, for instance, you have to check that if you have a if you have two matrices which are both the rows are finite and the columns not, two such matrices, and you multiply them, you can multiply them, but does the product have the same property? Okay, so there's an exercise, and that's it's good practice. Of course, it's not the only thing you should do, but it's good practice to invent exercises and take a look at. Well, I'm not saying you invented that, but you can make a choice to look at it. Okay, and you, in a sense, you invented it by entertaining this discussion. Okay, nobody's walked out. I mean, it's a bit it's a bit discursive discussion, right? I mean, this is supposed to be K-theory. So we're just talking of algebras and not just algebras. So where's the K-theory come in? Well, someone wrote to me. It was Chan Yi Zhou. He's on the lower. Is the what is the free floating? Why would you look at the free floating construction? Well, why would you look at infinite cardinals? Demoff wrote a children's book. Well, it's not really children, it's a high school level. 1, 2, 3, infinity. And he said this was actually very concrete. It was maybe in a less politically correct comment, which was common in those days. He said that there's a whole, he pointed out that there's a whole group, a whole tribe of Africans apparently that count that way, 1, 2, 3, infinity. But I guess children do, go up to a certain age. Okay, well, so infinity just meaning bigger than any number you can give a name to. So we know how to give a name to it. After a certain age, we know how to give a name to any finite number, right? And we maybe even have a motivation to do it. That's not clear what the motivation is. But we have a system. We supposedly have a system which is supposed to be able to give a name to any finite natural number, right? Okay, so that means we can, and we know how to compare two natural numbers, even well. Okay, but what does it mean to have a number which is not a natural number and that it's bigger than any natural number? I mean, it might not be bigger, it might lie between, might be halfway between two natural numbers, right? Okay, so the idea of numbers is already important. Of course, that's an important area of mathematics. So number systems is an important area of mathematics. The famous, the late John Conway, victim of the pandemic, one of the early ones, wrote a book called surreal numbers. Okay, so they're not real numbers; they're surreal numbers. It's a bit along the lines of Larry Smith's joke, but you can look it up, right? If you know how to, you don't even know how to spell. This is a terrible joke, but you only have to know how to spell surreal, right? Because the computer will do that for you. And well, it's that's I guess the basis of numbers is quite important, and Conway fits all known versions of number into his, including I guess imaginary numbers, into his system, and then some. Okay, so 2 times 2 is 4. That's my calculation of why you need four applications of the universal property to prove the uniqueness of the universal object. With respect to any universal property, you don't have to know what the nature of the diagram is that the test object respects. Okay, based on. Okay, but so what did Tierney mean, I wonder, by um, usefulness of the free floating algebra? Well, um, one reason for looking at the free floating algebra based on the um, on the on a given algebra is a pedagogical reason. Okay, if you look at the GLIM UHF algebras, you could say their classification is a bit too simple, too easy. If you want to have something a little more challenging, look at the free floating algebras based on them. Okay, and ask if it's possible to classify them. And and what's the answer, by the way? Carissa, would you say it's possible to classify there's some sense in which it makes sense to classify the free floating algebras, what I'm calling the free floating algebras based on UHF algebras? Okay. Does anyone can anyone recognize? Can anyone recall any aspect of our discussions up to now which might refer to that? Larry? Yes. Well, okay. So the UHF algebras, the classification is just the data in which they were constructed by, right? You have the supernatural number. You construct the infinite tensor product with those the matrix algebras of those prime power orders, right? Yeah, yeah. So that's one way to say it. Yeah, that the and in fact, if you don't have to go beyond talking about the supernatural numbers. You don't have to go beyond talking about the data, and you could say that this group is a one role it has is just a tool. I mean, you can express the theorem in terms of the group, which is very important, right? Because that's what generalizes. Okay, the K0 group. That together with the special element would be the number one, right? Okay, but if you if you just say that you just notice that group together with the well, has a concrete subgroup of Q containing Z, and you know what it is because you know what the number one is, but that determines the supernatural number. Well, then you can express the classification just purely in terms of the data, right? So data in, data out. You don't lose anything. Okay, but if you start with a piece of data, namely a supernatural number, and construct the UHF algebra, then go to the free floating algebra, the infinite matrices, which is finite many entries, the rest zeros. You How long it was off?
Not very long.
Okay, good. Yeah, good. Okay. Okay, so everyone knows what a functor is. What about a forgetful functor? Forgetful, well, okay, well, that's, I guess if it's not a forgetful functor, then in some sense it's a classification functor. I mean, it must, but I don't think that's the use made of it. I mean, so classification functor is what distinguishes isomorphism, non-isomorphic objects, right? It always takes any functor takes isomorphic objects into isomorphic objects. But if it takes non-isomorphic objects into non-isomorphic objects, then you can call it a classification function. And so the supernatural number, the function, the construction of a UHF algebra is a classification function because it takes distinct supernatural numbers. So it's a technical usage because we're talking about classifying supernatural numbers, and it's with respect to does the UHF algebra determine the supernatural numbers? Well, the answer is yes. You have two distinct supernatural numbers, then the UHF algebras are non-isomorphic, and the proof of that is you go to Larrey's group. That's a functor also, and if the supernatural numbers are distinct, then it's easy to see that the groups are distinct. Okay, that's a number theoretical question, nothing to do with algebra. So the which proves that the original functor is a classification functor. That's a purely number theoretic proof after you construct functors of class of Grimm's UHF classification. Purely number theoretical outline of it. Right. Still have to construct the function. But okay. Well, if you look at the floating algebra, then as Carissa points out, if you take the given supernatural number and you multiply it by 2, which will always be will almost always be different. It won't always be different, okay? Because if the original supernatural number is 2 to the infinity, then it's you multiply 2 to the infinity by 2, you get 2 to the infinity, and so the construction will give you the same thing. So it's not a question of 2 distinct supernatural numbers, but well, what's the important role? What's the important phenomenon involving the free-floating algebra? Well, the point is that they can be isomorphic with the when the algebras that they're based on are not. Okay, they can forget sometimes they can forget something. They can forget some things about the structure of the algebra they're based on. It's like looking through a telescope a bit. It's like looking at the base object through a telescope. You can't quite recognize all the details of it. But from a pedagogical point of view, that's very good because, in fact, the new isomorphism classes of the free-floating algebras, the Grimm UHF algebras, these are not even nicely, isomorphism classes are not nicely parametrized. The parameter space is the Cantor set modulo an equivalence relation, which is something like multiplying by 2. Multiplying by 2 is an example. And I suppose if you could go backwards too, equivalence relation is symmetric, right? So if if the second one is 2 times the first, or if the first one is 2 times the second, they're still going to give you isomorphic algebra. So I think it's a good exercise to find out exactly what this equivalence relation is and what the quotient space looks like. What are the I conjectured last time. I made the bold suggestion last time that the quotient space might be completely trivial. That no open sets except the empty set and the whole space. But in fact, there are open sets. Okay, so it's a good question. How many open sets? What are the open sets of the quotient space? Anyone look at that? But it's certainly not a Hausdorff topology. Everyone know what a Hausdorff space is? Okay. But so it's a good example of a non-Hausdorff topological space. Someone ever asked you what a good example of a non-Hausdorff topological space is? You can just say, well, look at the free floaters of UHF algebra. Look at the isomorphism class, the natural topology on the isomorphism class. That's non-Hausdorff. Well, okay, so, and at the same time, it's pedagogical in that sense. Also, it's pedagogical because it's a simpler invariant. In this UHF case, the invariant for the floating algebras, it's not, if you express it in terms of the group, it's not, you don't have to look at it as a group together with a special element, which determines it as a subgroup of Q as containing Z, right? You say the special element should go into the number 1. So basically, in Grimm's theorem, you're looking at the K0 group together with the special element coming from the class of the unit. But that's more complicated than just looking at the K0 group, right? So it's actually in a way the classification of the free floating UHF algebras, free floating algebras based on the UHF algebras. The classification of those is simpler. In a sense, it's simpler when you express it in terms of a functor, because instead of the invariant being a ordered group together with a special element, which ties it down to being a subgroup of Q containing Z, okay, and the special element is the number 1. You don't have to mention the number. You don't have to mention the number 1 when you're saying it contains number 1, right? Because there it is. It's there. Everyone knows what the number 1 is. Okay. As long as you don't get it mixed up with its additive inverse. That's a bête noire for me. If you can talk about -1 to mean -1, why doesn't anyone say +1? And why is it that the square roots of 1 are not called negative and +1 instead of plus or -1, right? So it's really an anomaly. It's something abnormal about this. And I blame it on misguided teaching, but I don't. Maybe it's better laid at the hands of fashion. It's just, fashion can be a helpful thing, but mostly it is. But obviously it can sometimes not be helpful. All right. So, this is the situation for AF algebras now. If you look at AF algebras, more general within UHF, that's where the finite stage algebras are not just full matrix algebras, they're finite direct sums of full matrix algebras over the scalars, over the complex numbers. And in this case, you have to keep track of the semigroup, the Murray van Herman semigroup, inside the. It turns out it's embedded inside the developing group, just as it is for for UHF. But so the invariant is K0 considered as an ordered group for the UHF algebras and their free floaters. Oh, right, okay. It's, okay, so I'm trying to make a case for looking at the free floating algebras. Another thing I'd like to look at is well, we have to keep reviewing the isomorphism theorem for AF algebras, and it's probably simplest. Well, I don't think it's too much of a not too much extra work to carry along the class of the unit.